jā. Labdien, man nodarbība.
Atstaga vajag, ne?
Kura?
Nu tā skapja, kur ir visi.
Nu tad tas nav degoši, es to skapi ieliku to un pamazam aizpildu. We will start in 10 minutes. Would you be available for consultation at 2 p.m.? Yeah, but for short time. I will end lecture at 2 for bachelors, and then at 2:30 I'll need to go to one more meeting. Yeah, I will be available 2 p.m. but for short time. Okay, what we need to do, we need to go forward. 1 second. It's time. Okay, let's do something. Where am I? Oh, here am I. Previously we spoke about Butterworth and Chebyshev filters, yeah? There is one problem with Butterworth filter is loved by many designs. Chebyshev filter also popular, not so loud, but loved. But all these designs has one weak point. What a weak point? Both Butterworth and Chebyshev do not behave well on sharp transients. if you expect to operate on sharp changing signals, you work on very what can be? You design very fast protection device where you need to react correctly on sharp changes. In this case, processing with Butterworth or Chebyshev, you will have problem. They overshoot. They seriously overshoot on sharp transients. And worst of that, if you fight for good in space of frequency, you need fast slow. Fast slow means high order of filter. The higher order of filter, the worse will be this overshoot. And this overshoot may produce false signal for your main logic. It's not good. For devices intended for fast operation, it's not good. Where to go? What to do? Special design is needed. If you think about operation on fast transients, you may need special design of analog preprocessing. Idea, you need your analog preprocessing part to have phase shift proportional to frequency. This can be achieved with special crafted special crafted filter. Base for such filter is a Bessel polynomial. Bessel polynomial series. You may find in literature Thomson's filters. Some scholars refer to such designs as a Thomson design. But generally, underlying mass is based on Bessel polynomial series. Development of Bessel series has roots inside Butterworth filter. It's development from Butterworth, but special development. We need to frequencies above this cutoff, this KNI frequency. We need minimum. Minimum depends on delay time for frequency from frequency for frequencies above this KNI frequency. Okay, if we assume simple your omega without constant shift, our transfer function of omega will be some zero transfer function divided 1 twice A1 Pn plus A2 Pn squared. Meaning maybe this can confuse B1, A and B. So my transfer function can be written as transfer function 0.1 plus omega A1 frequency minus B1 frequency square, but it's, be careful, it's a frequency in relative values to the knee frequency. Phase shift here will be minus arc tangents A1 normal frequency 1 minus B1 normal frequency squared, and delay time for the growth equals to minus phase shift, first derivative of phase shift to simplify things, normal growth time can be introduced. It is not profitable to calculate it in seconds. We can have this delay time multiplied by frequency, where this Fg is a filter cutoff frequency. So filter cutoff frequency multiplied by this group delay time. So group delay time can be minus group frequency, first derivative of filter phase shift by frequency. So we will have minus phase shift as a derivative from norm frequency. From this we will get what? We will get our delay time. If we would like to fight this overshoot, to how to say suppress overshoots, we need uniform from the exact in this parameter. So we will get our polynomial 1 plus B1 normal frequency square divided by 1 plus A1 square minus double B1 normal frequency square plus B1 square normal frequency in power 4. We will get system without overshoots if this parameter, so I would say better, to diminish overshoots we need to diminish dependence of this parameter from frequency. So minimum of overshoot will be minimum of T drop for frequencies above cutoff frequency. This will diminish overshoots. direct solution isn't very pleasant thing, but generally it's possible. If you have time and resources, you can start some numerical optimization process to obtain best A and B. Old school designs simplify process. If you have normal frequency much lesser than 1, you can use approximation for group delay time as A1 1 plus B1 omega naught squared divided by 1 plus A1 squared minus B1 normal frequency squared. But this is true only for frequencies, for all frequencies. This will be frequency independent. Frequency independent. When this will be frequency independent? Easy. This thing is frequency independent when B1 equals A1 minus double B1. So B1 should be approximately 1/3 of A1 squared. When it's true? It's true when square of magnitude of your transfer function is 1/2. For unity of norm frequency, so you will get 1/2, 1 divided 1 minus unit B1 squared plus A1 squared. This will yield you first Bessel's for A1 13617 and B1 06180. Nice. Further, direct solution isn't easy, but you can do step by step or recurrent formula. You will need C1, it will be 1, Ci can be formed as double n minus I plus 1 divided by I double n minus I plus 1. Here's your recurrent formula multiplied by I minus 1. You will get, in reality, you will get a set of Bessel polynomials. can get for any order, usually, usually no one uses polynomials higher than 4. So for first order, you will have 1 plus p1 and 1. For second order, Bessel polynomial yields 1 plus pn plus 1/3 pn square. For third order, Bessel polynomial is 1 plus norm frequency plus 2,5 normal frequency square plus 150 normal frequency in power 3, and for n4, Bessel polynomial series produces plus 3, 7 normal frequency square, it's a normal frequency, plus 221 normal frequency in power 3 plus 1/5 normal frequency in power 4. If needed, you can get higher orders, but usually no one goes beyond order 4. One thing with Bessel polynomials, usually when you go straight way, there will be one trick with these polynomials. What's the trick? Normal frequency base. This is complex frequency, but as a ratio to base. For Butterworth or Chebyshev filter, for simple low-pass filter, base to what frequency is normal is point of -3 decibel. For Bessel polynomials, it's different. For Bessel polynomials, are normal to the group delay time. I will, 1 second, I will find table for recalculated factors for recalculated to the point of -3 decibel. Usual straight Bessel design is different from Chebyshev Butterworth. Straight Bessel design uses no frequency as inversion of group delay time as a base for this Pn. expression of second order. I will be 1. A will be 1 for 6, 1, 7, B 1, 0, 6, 1, 8, 0. For N, 4. Okay, A1 will be 1, 3, 3, 9, 7. A2 will be 0, 7, 7, 4, 3. B1 0, 4, 8, 8, 9, and B2 will be 0, 3, 8, 9, 0. Oh. I will, if needed, you can okay. One tiny moment. We spoke on all pass filters before. If you have a good all pass filter design, you can easily convert it to high pass filter design, just replacing normal frequency to its inversion. So for your design, you will have infinite transfer function at infinite frequency divided by multiplication by I of 1 plus AI divided by normal frequency plus BI squared divided by square of normal frequency. This will be transfer function of your high pass filter. It's obtainable just as invert of LPF. What? in general, I have something as x from input as y from t. What I can describe as a low pass filter. So it has a characteristic like this. Frequency, magnitude of transfer function. General low pass filter suppresses high frequency, passes low frequency. In general transfer function will be 0, the complex value, divided by 1 plus A1 PF. This one is for first order filter. Filter like this is a first order filter. How to calculate order? How many reactive elements is in your filter? One capacitor, one reactive element. First order filter. 2, if DC factor is 1, H0, this one is ratio input output input at a frequency 0 at DC mode. A1 we can select as we like. Okay? Okay. This means what multiplication FC will be A1 divided by double T FG all first order low pass filters are equal. Any Bessel-Chebyshev Butterworth design yields the same. At the first order they are equal. For higher orders, this is not true. For higher orders, they will differ, but for first order, they are equal. Simple filter I draw has a disadvantage. Its frequency characteristics are dependent on load. If you would like to maintain your characteristic, what will you get? L1, C1, and you definitely may need a amplifier so here we have OX, we have get output. This part will convert full impedance for you. This makes, this is ground, this is also ground. Here, what we will get? Transfer function. What we will get? We will get R plus R3 divided by R3 also goes 1 plus grab delay omega F1 C1 and one more normal, it's normal frequency. Yep. Fine filter. What can we do? Can we make it even easier? If we do, what do we know about operation amplifier? Amplification factor is the, how to say, defined by what? By feedback. Yeah? If we put our frequency dependent network in feedback, we will get frequency dependent amplifier. Yeah? Which characteristic defined by our frequency dependent network. So if we put first order filter into feedback branch, we will get amplifier with frequency characteristic defined by our first order filter. As an example, F1 up to ground, and feedback should have F2 and capacitance. Here will be my output voltage, input voltage. Here, R1 should be 1 divided by double P group frequency A1 C1, it's a capacitance. And F2 should be minus R1 H at infinite frequency. Here's one thing you need to remember. In such schematics, you will have one thing behind curtains. It's a frequency characteristic of operation amplifier himself. Operation amplifiers do have frequency limited. So this works fine until your filter operation frequency is far beyond cutoff frequency, or is the drop in amplification by operation amplifier. We are lucky. In our case, common industrial operation amplifiers are working well because our frequency range is low. But if you apply this technique for when you may hit the wall, is a power line carrier. Idea when you need to when you try to use network for data transfer. In cases of PLC, you may hit wall at high frequencies because of required frequency correction for operation amplifier. You get how to say, two forces of same order. and you will go through iterative process. Design filter, apply characteristics of amplifier, redesign filter to correct. For cheap, I would say, okay, cheap not a good word. For common grade amplifiers, remember, they are start to going down after some 10 kilohertz. Okay, I have a couple minutes. First order filter is easy, simple, but first order filter will not, it's possible, but first order filter will not fulfill your requirement of to separation between go, not go, between pass and suppress. You may need second order. Actually, you repeat it, with analog, this analog field preprocessing with filter, you can buy a performance, you can ease a performance requirements for your digital part. Again, red line is 1/2 of your sampling frequency, or FD. This is red line, it's a Nyquist frequency. You should suppress any signals beyond this point. Here, it's all in frequency, is frequency range of your signal. Maximum frequency you need to process. This brown line is a required characteristic of your filter. So this space is your limit. You can use cheaper filter, it will go like this, first order filter. But this means what you need to move this red line to the left. And this one is determined by performance of your digital part. It's your digital processing performance. Okay, not 1, 2 minutes. I need to respond. Call from Institute Director. 1 second. I'll be back in 5 minutes.
Then when did you quit the job? Ah, okay. I think that was much better than this one. Lucky straight. Mm. Mm? Mm. That's better. Have you sent some email? Mm. Oh, do you have a class of that? I don't know. Mm. You are sending to. Mm. How many times? Mm. Mm. So, okay, I can add the one. No, no. Do you know the username? No? Okay. Actually, the cosmetics companies, Zindagi, do you know the product? Good. They are hiring the people, but not the long-term contract. They will give the 4 months or 6 months like that. After that, they will renew that. Mm, yeah, it's just normal. Uh, normal. Mm, I think now some people are working there. Their contract will expire on December, I think so. Maybe they will hire after the December because in December they have 15 days holiday for the Christmas. So they terminate the contract before the Christmas. You just make them. Maybe they will send the reply. Keep trying on the Sunday. They will have my 4 to 5 friends are working there already. You send the mail daily. You just schedule it. Mm. Did you get any reply? Did you try the mail? Basically, no increase in maybe they will hire another recruit instead of you. Like a business. come, we'll have a
It lasts 8 minutes.
hmm?
8 minutes more.
Yeah.
Not even 15.
Hmm. What was the next class?
12:30.
12:30.
Second class.
Did you come with first one?
Yeah.
What about the Akshay? He continued? No? He's still on first one?
First one like second
Second.
dynamic.
I think he's coming.
Mm.
And Rohit, he'll have to go at 12 o'clock. He will take the car till 12:15. Hmm? No, bro. I think everyone have a same problem.
Same problem.
Okay, we'll find a guy,
Okay.
and yeah, I think that's much better. Otherwise, we can't do this. Do you know how to do this?
No.
Okay. If you have any people, can you please search. We are 4 people. I think. How many taxis do you have? 5. Everybody is doing like this. Ask me. This guy, he have a appointment. I don't like rain. It's not good for that.
have money, but we don't have money. But in reality, we have money. Funny thing, when you have 1,000 accounts with 1 euro on each, okay, it's 10 euro each, you have 10,000 in theory, but you cannot use them simultaneously. Okay, it's our internal. Why? Okay, I'm back. I need to draw one more filter. I have bit of time. Yeah, so where we are? We need more distinguished border. We need better separation between area of signals and red line defined by our hardware, Nyquist frequency. Better separation will be what we need to do to get, let's say, it's frequency. It's a magnitude of my transfer function. If I like this slope sharper, I need to raise filter order. If I need something like this, get the second of or higher order filter. So, transfer of normalized frequency will be transfer at DC divided 1 plus A1 normal frequency plus B1 square of normalized frequency. Problem what divider will have conjugated roots, post max of transfer. In first approach, simple approach, passive approach, we will need to add coils into our filter design. So classical filter will look like this. Input voltage, coil, resistance, capacitor, and this will be our output signal. Here, transfer function will be 1 plus group omega, resistance, capacitance, sorry, what I'm doing, it's normal frequency, plus in divider group omega square LC normal frequency square. So for such filter, where they will be resistance A1 divided by double P FG and inductance B1 divided by 4P square F square capacitance. For, let's say, classics Butterworth, second order Butterworth. For second order Butterworth, F1 will be 1414, it's a classics of Butterworth, and B1, 1. Yes, 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 yes. Design, kill yourself. If F got for example, F got takes him 100 hertz. Capacitance, let's say 10 microfarads. For resistance, we will get what? We will get 2 to 5 ohms, but inductance will be approximately something like, wait second, 253 millihenry, something like this. It's plausible. In principle, this filter is plausible, but no one likes to deal with coils. Coils are expensive, and coils change their resistance from temperature. So, design, say, good practice of design is to avoid coils and use RC networks. Okay, for example, filter with multiple loops. One. This will be C2, F3. F2, amplifier minus, oops, this will go here, non-inverting to ground, yeah, here we have input, here we have output. Wait 1 second. Oh, yes. 1. Now correct. Capacitor 1, capacitor 2. This is second order filter. For this filter, its transfer function S will be L2 divided by L1 divided by 1 plus omega C1 plus L3 plus L2 L3 divided by L1 norm at frequency plus divider continuous omega square C1 C2 L2 L3 square of normal what I'm doing, square of normal frequency. Oh, here it's transfer. For this filter, it's a general independence. What we need? Butterworth, Chebyshev, and Besser. We need to specify A and B. So transfer at DC is minus L2 divided by L1. A1 omega C1 L2 plus L1 plus L2 L3 divided by L1 and B1. These are two equations. You solve them. Omega square C1 C2 L2 L3. So this you can have this equation you need to solve. Actually, you can start from resistance from standard rho. And what to do? What to do? Really, this filter is feasible for any positive A1, B1, so you can get any. You can get Besser, Chebyshev, or Butterworth, no problem. One only tricky moment. Because you have resistance and capacitors in standard rho, maybe usable to get these formulas. Usable to get these formulas. Where the trick is, For resistance, you have wider manual area than for capacitors. Capacitors are produced in, in lesser variety. Typical production, the standard production of line of capacitors is much stronger. You have less capacitance than resistance. Resistance are produced in step of tenths of percent. Capacitors are produced in each decimal. You will have only 6 values. Variance of capacitors is lesser. You cannot buy, for example, I don't know, 121 microfarads. They are not manufactured. 120 and 1 are manufactured, but 129 ohm is available without any problem. They are manufactured in mass, but capacitors, row of capacitance is much shorter. So it's usable to start from capacitors and then use this A1 C2 minus square root A1 square C2 square minus 4 C1 C2 B1 1 minus H0 H0 divided by 4P F gar, your cutoff frequency, C1, C2. L1 will be L2 divided by minus DC transfer, and F3 will be B1 4P square F gar square C1, C2, F2. Using this equation, I'm afraid I'm out of time. Next time I will show one very popular design. It's called Sallen-Key. Yeah, filter of Sallen-Key. When you need good filter, Sallen-Key often is choice number 1. Sallen-Key design is very popular. It's derived from bridge filter. For example, this device here stands. It's interesting device. It's a leveling function. On example, here it has magnetic fluid in this capsule, and inductance of both sides is measured. It uses Sallen-Key filter to extract signal. Funny device, I don't know, it may still work. It's put and deform. And can measure angle, or most what it do, it self-levels. And I should have its example, its schematic somewhere. I remember what it used Sallen-Key. Okay, next time I need to show one of the preferred design. It's a second order filter, but it works very well. It's a Sallen-Key. Higher orders, see, higher orders are dangerous, because at higher orders you may have it works it produces very good results at a poor point, but high order filters may be unstable. Usually when you need fourth order, if you have so narrow space between top frequency of your say pay your signal what you need to process and one half of your sampling frequency, if this border is so narrow what you need fourth order filter to separate them, maybe you should rethink your design. It's a dangerous situation. Yeah, it may be on what happens, you have